Hello, can you guys hear me okay? I'm on my iPad today. When I have a chance, I'll switch over back to my computer. Okay, does everyone see me okay? Let me see here. We have in the chat. Cool, awesome. All right, nice. Here, my wife is busy for the moment, so let me just let some people in. There's somebody hanging out here. Okay, let's go over some of the practice tests. Did you guys have any questions that you wanted to discuss? And I might not see your chats, so today, just for now, first of all, I'm on the iPad. It's better to just use the voice.
Some like questions on the practice test were a little confusing. So if you go over those, that'd be great.
Yeah, definitely.
Yeah, I can agree with that.
Okay, I'm gonna just download it and put it into Notability so I can write on it. Let me just pull it up here. But overall, was it okay? So was it all confusing or just a few handful?
There's like a handful. Like I got the first one, but like 2, 3, 4, and 5 were like, wait.
He hasn't even let me in the meeting yet, so.
Okay, let me see here. How do I open this? My drive, switch account. Okay. Let me see if I can share this. Open in Notability. Create new note. Okay, wonderful. I'm gonna just share my screen here. Zoom. Share contents, share screen. Start broadcast. And then Notability. Alrighty. Yeah, so which questions did you have a question about?
Number 2 was pretty, like, it was hard because I like did it, but I kept getting really weird answers. So I just decided to ask like for help instead of like doing it until, yeah.
Yeah, that's good. So the placeholders, I don't know if I emphasize that very much, but it's important when you're doing these, because you're on the 3x3 matrix, that you remember if there's no x and no y, you're going to write it like 2x plus 0y plus 3z equals 8. So we get rid of that one and write it like that. Did you do it that way?
Yeah, I did it that way, but like solving it, I like must have messed up somewhere because I got like a weird fraction. So.
Oh, it might have been. So for this one, because it's just the formula, maybe the answer is weird. So let me see. 1, 2, 1, and the augmented part is 5, 1, 8. Then 0, 3, minus 1, and then 2, 0, 3. And we want to use Cramer's rule. We don't need to worry about elimination or Gaussian row reduction, like messing around with the rows. We can just do the determinants. So did you get the determinant of this expression overall?
Yeah, it was something really weird. Like I erased it, but it was like 5, 6. So that's why I got confused because I didn't know if it was right or not.
Okay. Yes, that might have been correct. Yeah, sorry. For Cramer's rule, you might get a fraction because it's you only need to work with the whole numbers, like and your fraction will just show up at the very end. And that's really the nice thing about Cramer's rule is that, like, we saw that if when you're doing elimination and moving around the rows, if you start getting answers that are all like fractions and you can't get rid of them, then it gets really annoying. But the nice thing with Cramer's rule is, like, you have your numbers, you put them in, and then your final number might be a fraction, but that's no problem. So yeah, sorry for that confusion. I think Can you tell me the numbers you got? If or did you stop? You didn't go all the way.
I know for the bottom determinant I got 5, 6, but I erased the top one, so I'm just redoing it right now to see what I got.
Oh, hang on. You got it 5, 6 for determinant.
Yeah, that's why I was a little confused. Like when the x, did you because it says this look for x, so I did x over determinant 5, 1, 8, 2, 3, 0, 1, negative 1, 3, and then for the bottom determinant I did determinant 1, 0, 2, 2, 3, 0, 1, negative 1, 1, 3. It got 5, 6. That's why I got really confused.
Oh yeah. You got x equals 5, 6.
What?
Did you get x equals 5, 6? You got the number.
No, I got x equals 29 over 25. So.
Oh, okay. That's a little weird. Yeah, that could be a little. Okay, let's try it then. Yeah,
Okay.
we have, let's do it. And those of you who haven't had a chance to do this, please make sure you review how to do the determinants. So I'm going to write it here. Maybe give myself a little more space. 5, 1, 8. I replace the x column. 2, 3, 0, 1 minus 1, 3. And so I'm going to put that in the determinant here. And underneath it, I put the original one. Well, let's do it one at a time, and then we're just going to divide them. So let's see. If I put 5, 1, 8 and 2, 3, 0, if I multiply through here, it's going to be.
Sorry to interrupt you, but there's still some people in the waiting room. Like my sister hasn't been let in yet.
Yeah, thank you. Sorry, guys, because on the iPad I don't see everything. Participants. Oh, 4 people. Okay, awesome. Cool. Yeah, thanks for letting me know. Yeah, and if I miss something in the chat, if I'm not replying to your chat, I can't see the chats right now. So okay, yeah. So let's do this. This would be 9 times 5, which will be 45 here. Negative 16 here, and 0 over there. So those all together, 45 minus 16 is 29. Oh, did you do the other way up, going up too? So this will be 24 minus 5 and plus 6. That's going to be 25. Oh, okay. Now you have to subtract these two numbers. Remember, this number on the top is going to be negative. Or you put a minus sign in front, whatever it is, you subtract it. If it's negative, you add it. If it's positive, you subtract it. So you do, and this number on the bottom, you're gonna, keep it as it is. So combining those two numbers, the numerator on the top is equal to.
Would it not be -5 because of the 0?
Oh shoot! I didn't see. Yeah, that zero makes it. This will make it 30. Thank you. Thanks, Arthur. So this would be 30. So then I would get -1 here.
Do you always subtract it, like the two numbers?
Yeah, whatever, regardless of what the sign is, you're gonna take the bottom on the number on the bottom right, and you're gonna subtract the number on the top right. Now, I don't know what they might both be positive, one of them might be negative, whatever, but it's always the green number minus the resulting red number. And I want to just kind of like, one way I kind of remember it is it's similar to AB minus, minus the CD. This is plus, this will be subtracted. Gabby, did that clear up the mistake, or?
Yeah, I didn't realize that you had to subtract the bottom from the top, so I kind of just at random, so I got a really weird answer.
Okay, good. Yeah. So that's and it's good to practice these rules because like they're kind of just you know, a mechanical thing that you learn, and if you do it a few times, you get like muscle memory kind of in doing it. But if you just see me do it one time, you know that there's a rule and you know kind of how it works. But it's really good to practice it and make a mistake and do something like off and say, okay, it'll help you remember how to do it. Wonderful. And then are you okay to do that for the one without 518, the one that's just the regular one? Do you want to try that one just to confirm?
Yeah.
Okay. So does anyone object if okay, let me just actually, I don't want to erase. So I'll just put this one over here.
Could we just do this problem? Yeah, because I've been struggling with mainly the Kramer's rule with 3x3s.
Yeah. So with the Kramer's rule, which part of it, like with the calculating the determinant?
Yeah, mainly the determinant, and because I didn't know you were able to do the Kramer's rule if the timesing them all and putting and then adding them up and then finding the answer for. I didn't know you could do that with it.
Oh yeah. When we say Kramer's rule, we don't want to do elimination. We just want to plug it into this formula.
Okay, thank you. Yeah, just going over this whole will probably be of help.
Yeah. So okay, so let's do so we got -1 for the numerator. Let's do the denominator. The denominator is the regular matrix. So the denominator is the determinant of 1, 2, 1, 0, 3, -1, and 2, 0, 3. And this is not going to be too bad because I see these zeros here. And Archer made a good point that I always look for the zeros because that's going to be really nice when you multiply through diagonally. Okay, so I'm just going to do the method that I like. You don't need to do this method. If you like the other method with the plus minus plus, the Candy Crush method, stick with that method. Any method that you prefer is totally okay. Just whatever method you make less mistakes on. This method, you can easily make a mistake if you're not lined up correctly. And then I put 2, 3, 0. Okay. And now I get 9, -4, 0. And then multiplying, going up, so this way, this way, this way, I'm going to get 6, 0, 0. So 9 minus 4 is 5. So the bottom number is 5, positive 5. And the top number is 6. So I need to do 5 minus the top number, which is positive 6. So this one is going to be -1. So what that tells me is x is, and sorry that there's not some more space here. This tells me that x is going to be the determinant of the matrix with 5, 1, 8, whatever these guys are, divided by the determinant of the original matrix. This is -1 over -1, which is 1. Okay.
Wait, how did you get 6 for the top, like for the one on the top?
Okay,
like, I know how you multiply, but there's 6 because I got 12.
I might have made a mistake. Let me see.
I got 6 as well.
I think it's just because the zeros you have to be careful of.
Yeah.
Yeah, Gabby, do you see?
Oh wait, yeah, never mind. I didn't see that 0. Thank you.
No, that happens to me too with these. Like sometimes you just you're trying to multiply all these numbers and Yeah, you think the zeros, you do shortcuts in your head with like 1 and 0. Like 1, you ignore it, but 0, if you ignore it, yeah. So just be careful with the zeros, that they'll kill off an entire diagonal. Yeah, and if you want more practice, you can also do calculate y and calculate z. The nice thing is, to find y, you wouldn't need to do the entire process again. You only need to find the numerator, because the denominator would be the same.
For if you're trying to find the y, would you input the 518 into the second column then, and replace the 230 then?
Perfect, exactly.
Okay. Thank you.
Any other questions on number 2? Or number 1? Number 1 is the same thing. It's just instead of 3 by 3 determinants, it's 2 by 2, but it's the same pattern. Okay. How about 3? What did you guys think about 3?
I had no clue how to start 3.
Yeah, it's actually way easier than it seems. So, and there's like a shortcut rule to see what the answer is, but it's important to remember the trucks into the parking spots. So, what did we talk about? What needs to happen in order for one matrix to be able to multiply into another one? How is the multiplication going to be allowed? Do you remember the rule that we said has to happen when you do the trucks into the parking spots?
Don't they have to fit perfectly in?
Exactly. The truck has to match the size of the parking spot. Otherwise, it doesn't make sense. So, in other words, if I have a 2 by 3 matrix, and the rows is always the first number, the columns is the second number, and then I multiply that matrix, times times another matrix, what do I know ahead of time about the parking spots in the other matrix? The trucks are like, these are the trucks. What do I have to know about the parking spots in the other matrix? How big do the parking spots have to be?
3.
3. And I can have as many parking spots as I want. That doesn't matter. So here's an example of a 2 by 3 times a 3 by 5. Now, what's the result of what? And the reason it works is because the middle numbers, the middle dimensions, the number of columns, which is another fancy way of saying the size of the truck, of the left matrix is equal to the number of rows, which is a fancy way of saying the size of a parking spot of the right matrix. And do you see what the result would be? For each truck, how many spots does it have to park in? Each parking spot will give you a number. So each truck gives you how many numbers? Like the first truck, when it parks into every available parking spot, that tells you how many numbers in the first row of the answer. Anybody?
Sorry, still dropping out.
Oh, okay. Can you hear me though?
Someone in the chat said 5.
Yeah, we can
Uh,
draw it out.
yeah, yeah, exactly 5. Do you see that the truck parks into 5 parking spots? So like this truck here would go into 1, 2, 3, 4, 5. So the first truck gives you, you know, 5 possible answers. So the result would be, the shape of the result would be 1, 2, 3, 4, 5. And then the second truck would also park into 5 parking spots. Does that look okay?
So when you do these, can you pretty much just take whatever the first or whatever the columns are and then take whatever the spots are, and then that's just what the answer is going to be?
Let me think about that. Yes, exactly. So the shortcut is really easy. You take the middle number. If you do a 4 by 5 times a 5 by 2, you just have to check. Well, let me be more careful. You need to make sure that these numbers in the middle are the same, and then the result is just going to be a 4 by 2. You just pick off these last numbers. And I just wanted, you know, that's a rule that's pretty simple, but you know, it's important to know the pattern and kind of why that how matrix multiplication, how the mechanics of it works. How about the next question? Anyone want to volunteer? What does a 4 by 2 matrix give when you? What if you do a 4 by 2 times a 2 by 5? What would you get?
4 by
4 by 5.
A 4 by 5, yeah. And like you can just say it and like do the pattern, but actually take a moment to like maybe sketch it out in your mind, making sure that you see. In that case, we would have 4 small trucks, and they would park into 5 different spots. So you would have each truck in the first matrix on the left. You would have each truck parking 5 different times. So you have the first row is 5 numbers, the second row is 5 numbers, and so forth. So it's nice to visualize the actual process. But the rule is really simple. And be careful, the answer might be impossible, because if the middle numbers don't match up, then the answer is impossible.
So the middle numbers always have to match up.
Yes, because the trucks need to fit into the parking spots. Exactly. And then how did you guys, any other questions on number 4? Okay. How about number 4? Does anyone want to see it worked out? Or did you feel comfortable with it?
Could you work it out, please?
Yeah, of course. Okay. Let's see. So I'm just gonna kind of try my best. Like these, if you write everything down, it starts to look really messy. So I'm just gonna remind you what I'm doing. I take the first truck and I park it into each spot. And I'm gonna keep track of the numbers as my first row. And so you kind of look at your shapes, and this is a 2 by 3 times a 3 by 3. So therefore the result is gonna be a 2 by 3. So let's start. 3, -1, -1, 3, and the 0. That looks like the first number I'm going to get is -6. Then I do the first truck in the second row. That's going to be 3 times 1 minus 2 times -1 times 2. That's going to be a +1. And then the last one is 3, -1, 0 times 1, 1, 1. That's just going to be 3 minus 1, which is 2. Any questions on how I got the first row, or any objections?
Yeah, how did you get -6 from doing the 3, -1, 0 and the -1, 3, -1?
Yeah. Let's do it. So we have 3 already here. 3, -1, 0.
Do you
This -1, 3, -1. When I kind of park it in there, I get -3, 3 times -1 plus -1, yeah, that's fine. -1 times 3 plus 0 times -1. And that adds up to -6. Is that
No, not really. But okay. So do you do the 3 times the -1, and then for each one? Okay. Okay.
yeah? Do you see when I
3
when
and
I
the
park it?
-1, you multiply them together plus the -1 and the 3 multiplied together plus the -1 and the 0?
Like this?
Okay.
So you
Okay,
take
that
the truck. You got to take the truck is always driving in. This is like the front of the truck or whatever. You're always driving into the parking spot. It's head-in parking.
Okay, that makes a lot more sense. Thank you.
And then you do that for every one of them. Definitely. Any other questions about the? So how about I give you like a minute or two to do the same thing for the second row. So the truck 402, park that one into the remaining 3 spots. I'll give you guys a few minutes, and I'll go check out the chat and maybe just see. Let me know. Chat me when you're done. Zoom. Oh shoot! Sorry guys. There was 2 students that were waiting. Sorry about that. Conchita, I see you wrote something. Can you show the other method? Oh, the other method, the Candy Crush method for the determinant?
Yeah, for number 2.
Yeah, for number 2. Okay, yeah. Let's do one just to kind of review it. How to do the Candy Crush. That's a good idea. Okay. Anybody else need to be learned? Okay, looks like got in. Wonderful. All right. So let's go to back to notability. Okay, so anyone want to volunteer what numbers they got for the second row?
Yeah, sure. For the second row, I got -646.
I like it. Great. -646. Awesome. Anyone have any objections or questions about that one? Okay, great. So yeah, that's pretty much on this test. Most people get pretty high scores because I think the you just have to do the pattern. But I would like for you guys to try to do the extra credit, and I'll talk about that. But let me also do one. Let's try to find y using the Candy Crush method. So I'm going to copy this matrix here. Which one is it here? I'm just going to copy this here. Copy. Let's go down a little bit. Let's write it down. Oh, darn it. Maybe I need to select here. It's we found that the denominator was -1. The augmented matrix is 1, 2, 1, 5, 1, 8, and it's 0, 3, -1, and then 2, 0, 3. And let's copy and paste this. Copy. And let's just paste it down here. Okay. So to get y is going to be 102, 518, and then 1, -1, 3, And then we found the previous determinant 102, 2, 3, 0, 1, negative 1, 3. We already found that number to be negative 1. So what we need to find is the numerator. And let's do it with the Candy Crush method. Charger here. With the Candy Crush method, we would do this thing: 1, 0, 2, 5, 1, 8, 1, minus 1, 3. Remember to write plus, minus, plus. And now we're going to do 1 times the determinant of 1, minus 1, 8, 3, minus 5 times the determinant of 0, 2, minus 1, 3, then plus 1 times determinant 0, 1, 2, 8. Okay. So any questions so far? Is the Candy Crush okay?
Yeah.
Okay, so now we just do it. And I recommend just doing the determinants before multiplying it out. So 1 times 3 minus negative 8 will be, this will be negative, sorry, this will be a positive 11. Minus 5, this determinant, the 0 minus negative 2 is going to be plus 2. And the last one is minus 2. So it's 11 minus 10 minus 2, which is negative 1. So we get something nice here. We get negative 1. We get this negative 1. And so we get the overall thing as well. Any questions on the Candy Crush method? Just be careful, like where I would make mistakes generally on the Candy Crush method is getting confused when there's negatives in this diagonal, and like you got to sometimes take double negatives. So like you see 1 times 3, that's 3, minus negative 8 is positive 11. So just because there's like negatives floating around, don't forget the plus, minus, plus. That's really important. But other than that, you know, other than that, that's pretty much it. Any questions on anything else from the first 5 questions? Oh, sorry, from the first 4 questions.
I mean number 5, but that's it.
Okay, number 5. Let's do number 5. That's actually going to be a really fun one. So, and I didn't actually get to talk about the idea for number 5. I'll show you 2 more things. But before we go on to number 5, I just want to confirm anything with Cramer's rule, calculating a determinant, or matrix multiplication that you guys had any questions or needed some clarification on. Do you guys feel like you'll feel really confident that you can ace questions 1 through 4? Let's see here. Okay, sorry. In the chat. Awesome, great. Yes. Oh yeah, we're just doing. Okay, great. Okay, the chat looks good. Wonderful. Okay, So let me see. So please just hit yes. I'm looking at the chat now. Please hit yes if you feel ready to move on and you want to try to do number 5. Okay, cool. All right, let's do it. So number 5, I am going to show you a neat idea. And we kind of hinted at this already. So let A represent the matrix that's 90 degrees counterclockwise. Now, I don't want you to memorize what this is. Rather, I want you to understand how to find it. So remember the picture. This is from a previous example. If we write, this is E1, and this is E2, a 90-degree rotation just transforms it. If you do a mapping by multiplying by A, the 90-degree transformation moves E1 directly up. This would be AE1, and then this is AE2. And I'm kind of drawing a static picture here, but I really like to, let me see if I can do this. You know, all these pictures that I've done, let me see here. Copy, paste. Yeah, I'm really thinking, like every time I'm doing one of these, in my mind, I'm actually thinking of moving. This is actually really cool. I'm thinking of doing this to my shape. Do you guys like that? That's pretty cool, right? I should have done that.
So each A, so like to the power of whatever is just that many rotations of it.
Exactly. So now we can do this problem in 2 ways. One way is really, really annoying, but the other way is awesome. It just takes a second to look at the picture. So first, what is A? A, the column of A, remember, is what happens to the column of A is equal to what happens to the AE1. So that's going to be 0, 1. This is the AE1. Because remember, when E1, the nice thing about the standard basis E1, E2 is that if you look at a matrix, you can say, oh, the first column is where E1 gets sent to, and the second column is where E2 gets sent to. It's just the way matrix multiplication works. It was almost as if that's how it's defined. And it happens to fit in this like truck into the parking spot method, but really that's all it's saying. That's matrix, that's all it really represents. And AE2 represents the information of what happens to the red vector. And that red vector goes to -1, 0. Okay, now if you wanted to, we did earlier, we found out that A squared equals 0, 1, -1, 0, 0, 1, -1, 0. When you do the parking spots, trucks into the parking spots, you know, into the here and here, what you end up with is you get A squared is -1, 0, 0, -1. Which shouldn't be that surprising because if you do 290 degrees, you get to a 180 degree. If you want to now do A cubed, you can do the same thing. You can do A squared times A. Or rather, either way is fine, it doesn't matter because it's still going to be A cubed. So we can do, I'm going to write it a little bit differently because the reason I'm going to write it is when we do operations on matrices, you always want to do the newest operation, the newest move on the left. So -1, sorry, So I'm going to do this. This is doing it the long way. You don't have to do this way. In fact, you shouldn't do it this way. But I'm just showing you why it's useful to think about the geometry and what's really happening here. Okay, I'll give you guys a few minutes to do this out by hand. Just do it carefully and tell me what you get, or tell me when you're done. I'll let you write it down, and then we can do it together. Let me see, go back to Zoom. Yeah, just message me when you're done. And if you want, I can go back to that screen. Nice guys, nice Gabby. Oh yeah, okay. Are chats available to everyone? Okay, yeah, everyone's available. Awesome. Okay. So let's see if you could, got it. Let me, let me go back and I'll do it carefully. I probably should have told you the format to write it in. Okay, so when we do this first truck, and we're gonna, I like to stick with my truck one at a time. So the first truck into the first spot, the zeros and ones kind of miss each other. So that's going to be a 0. And the next one, the negative ones hit each other and the zeros hit each other. So that's just going to be a 1. The second truck is going to be -1. And then the next, so this is going to be -1. But then the last spot, the ones and zeros miss each other. So that'll be this, -1, 0. This is equal to a to the 3rd. All right. Any questions on the matrix multiplication? All right. Archer, do you want to try to explain how we could have gotten this in a second without doing any matrix multiplication?
By drawing it out?
Yeah, and so how would we do that?
I mean, as you showed, you could just basically think of it as rotating it each time, and if it's counterclockwise, that would mean it would basically be a 270-degree turn counterclockwise.
Exactly. Let me see if I can paste this. And oh, darn it.
Wouldn't 5 just be the full 360, but then one extra turn? So it's just basically 1?
Exactly. That's right. So let's look at this. So this is if you take this pair, this your grid, there's a grid underneath here, right? It's like the green and red arrow determine a grid. If you take your grid and you rotate it 270, I'm messing it up by stretching, but if I rotate it 270 degrees, it turns into that. And so the first column has to be representing the green arrow, and the green arrow is just pointing down 1 unit. So that's 0, -1. And the red arrow is pointing to the right 1 unit. That's just 1, 0. That's it. Well, what do you guys think?
Makes a lot of sense. It's mainly just
Right.
the part that is confusing.
Is the what that's confusing?
The matrix part of it.
Yes, that's right. Underneath matrices, at least simple, like the matrices also do something else called, like I mentioned, the shear thing, which is like squeezing the grid together a little bit, turning the squares into parallelograms. If you kind of, if you don't turn the red and green thing by the same angle, you can. I wish I could draw. I just need to post that video. Maybe I can share a video of it. But it's just like stretching out a a square into a parallelogram. That's one of the complicated things, but the other things that you can do with these matrices are really simple. It's really nice to think of them as nothing more complicated than moving your piece of paper, just like zooming in. You can zoom in, zoom out. You can and rotate and stuff. The one thing you can't do with matrices is you can't translate, but you can do rotations, and also I can't do it with my fingers, but you can do reflections as well, and you can do shears. But that's it. Okay. And then yeah. So Archer, if you go a to the fifth, what would that be? By that logic.
Then it would just be a single counterclockwise change from the original, since
Right.
we're full 360.
Exactly. So if you do 4 turns, if you do a to the fourth, so a to the fourth, you're back to where you started. Therefore, a to the fourth is just 1, 0, 0, 1, which is do you guys remember what this matrix is called? Starts with an I.
Identity matrix.
Perfect. Identity matrix. So is it clear that if you rotate something with 4 90-degree counterclockwise turns, you've done nothing to the shape? Because it's back where it was. And if you do a to the fifth, well, that's the same as exactly 1 counterclockwise turn. So that would be 0, 1, negative 1, 0. Or in other words, this would just be a.
So basically every 4 is completely reset to its original space.
Correct, exactly. And keep this, I really like this example. There's something we'll see at the end of the course, a really big surprise related to this example. But it's really cool. 90-degree rotation, you can represent it as a matrix, and it has these nice properties. And by the way, all of these matrices, if you calculate the determinant, can you guys tell me what the determinant of each of these matrices is? Like a squared, a cubed, a to the fourth, a to the fifth? Like what's the determinant of a? So here's a. Really quick, what's the determinant of a? We do 0, 0 minus 1, negative 1. What do we get?
-1.
Be careful.
Positive one.
Whoops.
Positive, because it's minus, that's minus this negative. I make that mistake a lot. So it's this guy minus this one, so that negative turns positive. So it's actually positive 1. So remember what we talked about, and let's do the other ones too. Determinant of a squared. What's the determinant of a squared? If this is a squared, the determinant is this one minus this.
Just one again.
It's just one again. Now, remember the determinant told us how the fundamental square of our grid changed by what factor it changed. Whenever we rotate, do we change the size of our unit square? Does the unit square that gets the new unit square, that like the new fundamental parallelogram, does it change its shape at all, or area? It doesn't change its area. It's always the same 1 by 1 square. And I mean, it could actually change its shape, but it doesn't even change its shape. But the determinant just measures how much of the area has changed. And each time the area doesn't change at all. So that's why the determinant of all of these rotation matrices, these are a special case of rotating by 90 degrees. This is a special thing called the rotation matrix. When you learn trigonometry, you'll learn how to do it, how to express a rotation matrix using the trig functions cosine and sine. Yeah, this is a nice thing to know. Now, I'm going to ask an interesting question. So we saw when we were doing these determinants that you can also get negative numbers. These were for a 3 by 3, but you can also potentially get a negative for a 2 by 2. Does anyone want to try to explain how the heck you can get a negative determinant? And if the determinant represents the area of the new grid, the new fundamental like grid square, then how the heck can you get a negative? Anyone want to just take a wild guess? What the heck could a negative determinant possibly mean? Let me see if there's anybody wrote anything in the chat. Any thoughts? How could we have what the heck? We said the number that the determinant equals is the represents like the scaling of the area. What do we mean to have a negative area? And just take a guess. Let's hear at least one guess. And you can message me in chat also. And it's a very interesting idea because it extends to something really cool in 3 dimensions also. Any guesses? Okay, let me show you an example. It's really simple. So let's do one more of these. So let A represent the matrix that reflects in the line y equals x. So let's try to picture what that does. Line y equals x. What angle does that go through? What angle does that look like? So I draw my green one, draw my red one. How should I draw y equals x? What does it look like? Any volunteers? Oh, can you guys hear me okay?
Yeah, we could hear you.
Okay, yeah, what is y equals x? That's just down the middle, right?
Yeah.
Okay, what happens to the green arrow when I flip it over the line y equals x? Yeah, just somebody shout out. It's not just me talking.
Doesn't it become negative? Like the green line will like become negative, I think.
Well, let me think. It doesn't become quite negative, but imagine kind of tilting your head to the left. Can you see like the reflection? Like whenever you reflect.
Doesn't it become, you like go on top of the red one?
Exactly. It's like you're reflecting like this. you're spinning the green line, like you have a piece of paper, and this is like a skewer or a piece of metal or something, and you're just flipping, you're spinning the skewer or the wire or whatever. The green line will turn into the red line, and what will happen to the red line?
It
The green
becomes
line-
the green line?
Exactly. Does everyone see that? It's really simple, but I like it. I don't know. So they just swapped. Okay, let's write the matrix for this. So what is the first column going to be? What is the first column?
Would it be 0, 1, 0?
Well, so 1, 0 is the original one, but it got changed.
Oh,
So
it'd be
now
so 0, 1,
0, 1, and the second column therefore is
1, 0.
perfect. So this is a really just fancy matrix. It's a simple matrix, so it's a fancy way of just saying if you have any point like floating in space, like let's say right here. So this point is x, y. When you flip it over, it moves over here. It becomes y. Maybe instead of x, y, let me do a different letter, like a, b or something. Then it moves over here, it becomes BA. And that's what this matrix does to any vector. It switches the x coordinate and y coordinate with each other. Okay, what's the determinant of this matrix?
Is it 1?
Not 1. It doesn't change the size of the grid, but let's actually calculate the determinant. What does it come out to? 0, 0, right? But here we have a minus sign because it's going from the bottom left to the top right.
So it's 0?
Not 0,
Oh,
but
it's negative 1.
got it, nice. So now that you've seen this, how can you interpret a negative determinant? Why is this determinant negative, and why does that kind of make sense? Even though the area hasn't changed, what has sort of changed about this grid? Imagine you have a piece of paper, basically, if you imagine the plane as a piece of paper with like, I don't know how I could draw it, but there's like a piece of paper and the front of it is purple, but the back part, let me see if I can kind of, I'm gonna make my maybe something make it more confusing, but you're just flipping the piece of paper. Do you guys see that the only way to turn the green and red arrow from one to the other is to basically the only way to turn one grid into the other is you have to go to the back of the paper. Like imagine your XY plane was like had thickness, was an actual piece of paper, and the front of it was the front of it was blue and the back of it was yellow. When you do a reflection, you see the yellow part. And then if you do another reflection, you go back to the blue part. So the reflection, or the determinant being -1, means you're somehow seeing another orientation. You're seeing your entire space from another perspective, or from a backwards perspective. And there's a similar thing in 3 dimensions, where if I have 3 arrows floating in 3 dimensions, oops, sorry. Did that idea make sense? Like that the paper, like when you flip something over, it's called you're changing the orientation of the paper. Like rather than looking at rather than looking at it from the front, when you flip it, you can think of it as looking at it from the back. And so that's why there's a negative determinant. That's what the negative sign represents. And I'll just show you with a 3D what that kind of does. Have any of you, and it's okay if you haven't, or just curious, have any of you heard of the right-hand rule and the right-hand rule in physics?
I don't think so.
Okay, the right-hand rule in physics is something to do with like electricity and magnetism, and it's kind of like also it's related as well, I believe, to have you guys heard about the thing with the well, maybe not. Let me think about that. I'll take that back. I was going to say it's related to you've heard about the thing with the toilet bowl, like that it spins a certain way in the northern hemisphere.
I've heard about that. Is
Yeah.
it true?
It is true, yeah. But it's actually not. It is not. I don't think it's actually related to what I'm about to show you. But I have to think. I mentioned it because it's related. Kind of has to something rotating, but I have to think a little bit about it. But anyhow, in 3 dimensions, you can have. So imagine this is like kind of like in 3D space. This is E1, E2 is over here. So you have like a, you have your grid right here. This is in 2D, but I'm looking at it from a slightly different perspective. And then I can also go up, and I can get my 3D space. You got your 3D space here. So I'm just doing this like the shaded lines, but so E3 could be a purple line. So this is E3. Do you guys see kind of that those 3 vectors in 3 dimensions? E1 in 3 dimensions is, and this is related to 3 by 3 matrices. E1 is going to be 1, 0, 0. E2 is equal to 0, 1, 0. And E3 is equal to E3 is equal to 0, 0, 1. So those are the standard bases. And we saw, like we did previously, a 3 by 3 matrix we found as determinant. What this matrix really represents is moving E1 and E2, moving E1 over here, moving E2 to this vector, and moving E3 to this one. And that creates that weird like 3D parallelogram, we call it parallelepiped. Now, it turned out that the matrix had a negative determinant. So the negative determinant, tell me what you guys think about these 2 shapes that I'm about to draw. So the one way to think about a positive determinant is you're just stretching the shape, but you're not doing anything, like you don't need to flip it out, or like you don't need to take it inside out or do anything weird. You can get it by just maybe, you could take a real shape and you could actually move it around, maybe stretch it in one direction, but you don't need to do anything where it kind of goes through itself. For example, imagine this is my green one, this is my red one, right there, pointing out, and the purple one points up, like that. What do you guys think? Can I go from the original standard basis to the new vectors pointing in 3D space? Can I do that? So this is pointing kind of like, also there's little weird illusions I can draw here. So, but this would be like, there's a draw like that. So can I go from the unit cube to that box just by doing a rotation and some maybe stretching, squeezing together some of the sides or stretching some of them out? Would that be doable? What do you guys think? As compared to the following example, what if I do something like, let me see here. Yeah, what if I do the following? No. So this is going down. This one is coming out, and this one is red. So this time I have a little grid like this here. So do you guys see any difference between the drawing on the left and the drawing on the right?
Aren't they all just rotations?
Let me see here. Yeah, the first one is like a rotation for sure, just tilting it a little bit. But the second one, if you try to, and this is a little bit, you really have to visualize the move. But if you try to move this guy to match up with this shape, then look at the base. This is like the original base. This is the base right here. But over here, the base is here, right? Now imagine trying to move the base, put the base on there, but now you want the purple arrow to point down. No matter how you try to put the green and red arrows on top of each other, the purple arrow from the original thing will never point down. Or alternatively, can you see that if you take the purple arrow and you try to point it in this direction, the green and red arrow will have been switched. So if you take something in 3D space and you take the z-axis and you point it down like that, then the red one will have to be like over here and the green one gets moved over there. This would be a rotation. This would be this would be an allowable rotation. Because when you move the red one down, imagine you have three, let me go back to video. Cancel. Zoom. Let me stop share. So imagine these are my three axes, right? This. If I want my index finger, which is my z-axis, if I want that finger to point down, then when I do that, my thumb and my middle finger switch. It's terrible. Yeah. So you can. That's the idea. So they switch their positions. So if you're drawing a picture where the red and green are not switched, then the only way to really do that is to kind of move the shape through itself. You're kind of like you're reflecting one of the arrows through the other shape, and that would be creating a negative determinant. So this idea of positive determinants means that you can get from one shape to the other without collapsing your shape somehow or without doing some sort of reflection. But whenever there's some sort of reflection that's required, you're going to get a negative determinant. And the other cool thing that if you continue learning about matrices that you'll see is that when you take a matrix and then multiply it by another matrix, that represents doing two things one after the other. And so what happens with the determinants is that they'll multiply. If you stretch a grid by the area of a grid by 5, and then you stretch it by 4, the overall grid will stretch by 20. Okay, do you guys have any questions? Sammy has been asleep the whole time. You did really good. Let's see here. All right, guys. Any questions about anything from the test? So, do you feel okay to do the test on Monday?
Yeah.
Okay, wonderful. Yeah, let's do the test on Monday, and yeah, and then we'll start some new stuff. We'll go slow on the new stuff. I think it's gonna be like parabolas and it shouldn't be too bad. But I also want to give a chance. Like there are about like 10 people or so that still need to retake the second test. So I want to maybe you know definitely give you guys um, yeah, I'll post the notes that I have. I'll post them today. But make sure for the test that you learn how to do the matrix multiplication and the determinant and all that stuff. But yeah, you guys can. Jackie, I'll try to post this recording as soon as possible. It's just tough sometimes with the recordings because I need to process them a little bit. But yeah, I'll get these up. All right, guys.
Thank you.
Have a great rest of your day.
Have a great rest of your day. Have a good weekend.
Bye. Have
Yeah.
a good weekend. Thank you.
Bye, guys.
Bye. Thank you.
You're welcome. See you. Good luck.
Thank you.